Well, hello, good afternoon. Guan, first of all, thank you for introduction and thank you for inviting me to do this talk. So as you mentioned today, I would like to talk a little bit about the past work that we have done and then the recent work we have been doing in the area of underwater systems. And then the title that is towards software-defined underwater network systems. And I hope that title will mean much after I went through my slides, so we can actually understand what is that the software-defined and networking would do for underwater systems for us. So I think the first thing where we need to start is that obviously the question that you might just come up with is, why do we need actually underwater networks, right? Why would be important to have underwater connectivity or underwater networks? So underwater networking has been primarily used in military domain in the past since World War II. You can just, if you have ever seen a movie from the past, that you can see that there are operators sitting in submarines and listening to other submarines, or like trying to identify boats, and then just send few bits of data here and there, just distress signal in most cases. But today, with the evolving applications and evolving needs, there are many different needs, and the underwater underwater networking, to be specific, actually becoming a enabling technology for many of the blue economy applications. Obviously, still it is very important for military, but much more than this, sending a few bits of data, distress data. It's more used for underwater surveillance, so you can just monitor different shipyards, ports. You can have real-time video streamed from UUVs or divers even, to be able to monitor and do operations that can be controlled, as we are pretty much doing in the aerial drones, to do the same thing in underwater, but without having cables. The other applications, and that is primarily is really up and coming, is the offshore equipment monitoring. There are different platforms that we're building today in offshore. The first one is the oil and gas platforms, which has been historically be deployed there. So there is pipelines, there is offshore platforms that is always prone to a failure, and then it can create a crisis like it happened back in the early 2000s in Gulf of Mexico, that really end up in an environmental disaster. So underwater networking systems can actually detect these type of failures in real time and can detect it. There are also new types of offshore equipment monitors. There's offshore wind farms, which is currently being deployed in the Martha's Vineyard in the south of Boston, actually. There are many different offshore wind farms that is built all over the world, but today we don't really know how the wind farms are affecting the marine life, how they're affecting the flora of the oceans, what are the challenges there. So there are some regulations, and that's why underwater networking capabilities, sensing capabilities become very important, so that you can actually have marine life detection. You can anticipate and forecast the effects of these wind farms to the ocean environment, as well as you're able to see the health of the equipment monitored over time. So these are pretty much today's need at this point, rather than just future needs. And last but not least, there is also quite a bit of need in the aquaculture domain and data-driven fisheries. As you may be aware, that we are now moving towards a data-driven future rather than a model-driven future. In the past, we had models and we were using some basic models to do things. Now we have AI, larger processing powers. So what we do is that we use data to learn, to adapt, and to also decide. So we need that data in real time to give data-driven decisions. And aquaculture is not short on that. We have a ton of data that needs to be extracted from aquaculture, from fisheries in real time, to be able to enable more efficient, more environmental friendly, and more, let's say, producing in more inefficient way fish and shellfish, whatever you're producing, is a big need. And that is primarily important in US because actually we're consuming much more than we produce. So we have around $1.7 billion of seafood deficit, actually 16 billion seafood deficit. So that's a huge number. That is pretty much US is buying from external sources. So there's quite a bit of work that is going on in the fisheries and aquaculture, and there's quite a bit of different startups looking into that as well, including like the companies from X, which is the Google's moonshot factory, like the Tidal is looking into that for instance. So as you can see, there are many different applications. So the system needs are evolving. There are different needs from the applications, from the environment that you're deploying. So everything becomes more increasing and complex and diverse. So in a sense, while it's a good thing that we need more in underwater networking, it is also challenging to address all these applications and all these requirements that we have. One other thing that I would like to mention is that also there are also many different type of applications, which we would like to call it like joint all domain command and control. So in a sense, it's creating connection between different domains to be able to create opportunities to sense or act in a harmonious way with the data from different domains, or operate with the data from different domains in a sense. And what, sorry, that it just switched for some reason. And what we really want to connect here is that the water domain with the aerial terrestrial domain. So making the underwater domain part of the Internet of Things that we are building in the rest of the terrestrial domain, and then being able to make this connection between the digital world and the oceans. But with today's technology, it's very hard to do that, and it's very hard to have networks that can span different domains, including the underwater domain and the aerial domains that we are primarily looking at. So if we move a little bit into the challenges, so why we don't really have this today, what is stopping us, and what is really challenging here is that if you look at it into details today, I mean, in underwater domain, primarily we are using acoustic and ultrasound signals. And the main reason is, a good reason for that is because if you try to use the radio frequency waves, which we use in terrestrial domain communications, in 5G, Wi-Fi, Bluetooth, which you're doing it and using it every day without even noticing and without pretty much taking for granted, they don't really work in underwater. And that is primarily based on the basic physics. These waves are dispersed in underwater, they're absorbed, so they cannot propagate further in the distances. So primarily the main carrier in underwater domain is acoustics. However, there are some certain challenges and some unique challenges in acoustic channels in underwater. So first of all, the propagation of sound is much slower in water compared to a speed of light or electromagnetic signals moving in RF domain. So to give you a sense, it's 6 orders of magnitude or 5 orders of magnitude slower propagation speeds are appearing in the sound propagation in underwater, which reduce the network throughput considerably, and it also add quite a bit of delay onto the device that you're designing. One other thing that is really important and is very interesting is that there is not really models in underwater acoustic channels. So in RF channels, if you're familiar, there is Rayleigh models, there's Ricin fading models. So you can actually use some basic models to generate and create a digital twin even of an environment. And most of those time, that environment is not really changing from an area to area or from time to time. But these channels actually constantly changing because there are currents moving, there's tides are coming, the channels are changing. So it's been always made joke is that in that domain it's impossible to find the same channel twice in underwater domain. It's always changing, it's always creating new challenges for you to address. The next thing is very unique is that pretty much in every environment, there is a multipath effect. So multipath effect you will see in RF domain in indoor environments. So there's reflections from different sources because underwater domains are bounded by a surface and bottom. You will always have reflections coming at most times from the bottom and surface, and you will get severe intersymbol interference, and then your receivers needs to be addressing those designs in a sense that needs to be designed specifically for these multi-path effects. Obviously, noise is also very important in underwater domain. So noise is pretty unique if you look into it. It is really not white. It is a very colored noise, and it is appearing in different parts of the frequency by different sources. That could be man-made sources like machinery pumps or shipping activity, or it could be ambient noises like seismic activities or waves and currents and tides. One other thing that it is really important here to understand, there is not a really FCC. So there's no one regulating the underwater acoustic channels. So anybody can transmit anything at any power that they like at any frequency at any time. So this is, for instance, a recording that we had got a few months back in Boston Harbor. And when you look at it, you're just seeing, okay, there's not really any source around, so you wouldn't expect to have any sorts of noise. But when you look into the spectrogram, you can see that there is pulses in many different frequencies. There is linear frequency modulations, chirps in different in different frequencies. So it's a very crowded bandwidth and spectrum because it's really not coordinated, or it's not very regulated. So pretty much you're dealing with in a very hostile environment to be able to communicate in this domain. And then what is really important here is that if you look at it, it's actually quite limited in the bandwidth as well. And I will explain why that is the case also in the next slide. So if you look at it in underwater acoustic channel, we have a huge high path loss. And the high path loss, the path loss is also increasing with the frequency in a geometric way. So if you go higher in the frequencies, you will get more and more path loss, that your range will be limited. So this is in a sense really limiting the bandwidth that is available for communication. So at most times you're looking into few tens or few hundreds of kilohertz bandwidths. And if you're very, very lucky, and if you're very short in distance and there's like a super isolated environment, then you're getting few megahertz bandwidths in this domain. So that compared to a standard Wi-Fi, which is around 20 megahertz in 2.4 gigahertz Wi-Fi, it is really, really slow. So your data rates is very low. And so that means is that you have to be really aware of your spectrum resources, and you have to be really, really getting that spectrum efficiency in place and being able to address these, to use these channels efficiently. One other effect, which is also very prominent in underwater domain, is Doppler spread. So Doppler spread and Doppler effect, I'm pretty sure that you have heard about it before, is that happens due to the movement of the noise source. So if you're just going towards the observer, right, your frequencies get higher. If you're going away from the observer, your frequencies get lower. So in a sense, the original frequency that you're sending is changing and shifting depending on how much speed that you're having relative to your observer. Normally, you won't really hear about Doppler effect in RF domain. And there's a good reason for that, because there is speed of light, so we cannot move as close to the speed of light. So this means is that factor of relative speed is negligible, and you don't really see much of a frequency shift. But because the speed of light is slower in underwater domains, even few meters per second movements is becoming really, really pronounced in underwater domains. So that if you have a frequency that is 100 kilohertz, and then you're just imagine that you're moving a platform in underwater with 3 meters per second, then you are seeing almost few tens of kilohertz shifts on top of your signal. So your signal is getting spread around. And then because it's also frequency dependent, every frequency band that you're transmitting is getting a different frequency band. So they're creating intercarrier interferences, or they're spreading all around that you cannot control. So the receivers needs to be aware of that. And it's actually one of the most challenging tasks in underwater domain to be addressing these Doppler effects. And last but not least, there is also can be shadow zones in underwater domain. So the sound waves, the acoustic waves that we use tend to converge towards where the sound speed is slow. And I was telling that the sound speed can change in environment to environment because the channel is varying. So you can see that on the bottom, there is a sound speed profile. You can see at the surface, the sound speed is slower than towards the duct. And if you go deeper, the sound speed gets slower. So this acoustic waves, we call them, they're lazy. They're always converging towards where the sound speed profile is. So the sound speed profile is low. So that's why you can see that all those waves, we're expecting that it will just spread around evenly after they were transmitted. They're actually converging towards where the sound speed is slower. And then you're creating that, what we call shadows. So even if you're just seeing your observer and then you're saying that, okay, I should be able to receive signals, you might not be able to receive those signals. And that's one of the biggest challenges in underwater domain as well. So overall, as you can see, there's a lot of different challenges, a lot of different effects that you need to account for. And all of those things are actually changing from time and space. So what we really need is that we really need that reconfigurable, programmable architectures that we can actually adapt the devices to satisfy that environmental application and system needs. So that is something that was the core of our research that we were doing and core of our idea of our spin-off as well that we've been working. So if you look into today's technology, there are some limitations. So if you look in and you try to buy, for example, an underwater acoustic communication device out there, most of the devices are monolithic architectures. So they're hardware-based. What that means is that they are basically, their network infrastructure are totally intertwined with the hardware architecture they have. So they're basically inseparable from the hardware. And that makes them very hard to update, improve, or reconfigure the drivers based on the environment that you're operating. So it's impossible to reconfigure them. They also always focus on more on the lower data rates. They don't really support most of the applications that's out there, and that is enabling for the blue economy. And they can be also very large, not very cost efficient, and not very energy efficient. So those are the current limitations of today's technology. Then if you're looking from an architectural perspective, the lack of the network abstractions today in underwater domain does not exist. So we're lacking this network abstraction. So most of the links are looking into the point-to-point links. There is not a development abstraction. There is not abstractions to implement cross-layer control algorithms. And as a result, there's also not sufficient enough spectrum agility to be able to shift frequencies or to be able to implement arbitrary waveforms or new keying schemes. There's not a real support for dynamic spectrum access. And this is really, really limiting what is today's technology to be able to enable and address most of the applications that we're looking. And last but not least, there is not really a connectivity and compatibility with the standard internet. So with today's devices, it's impossible to make these devices to be IP addressable or being able to connect them through with the standard internet if you look into them. So to address these challenges and to see the large opportunity of applications that is coming up, in recent years, we had a project that was supported by DARPA, by National Science Foundation initially, and then at the company side at DARPA. And what this initial project was funded by National Science Foundation was called CNET, Underwater Network. So this is a collaborative project which recently finished last year. And this project was aiming to build software-defined network systems and advanced AI algorithms for underwater communication services that can be built on this modular architecture of the modems. And what was primarily intended in this project was to address all these limitations and the applications, and to that end, to be able to provide high-speed data rates for underwater assets, to be able to have full-stack internet-compatible networking on each device, to implement modern software-defined architectures, to be able to enable mesh networks and mobile and static elements, to be able to have AI-based control and data analytics on each devices, to also enable all network nodes to be able to reprogram remotely and then being able to adapt themselves to the new network behavior. So overall, the goal was to have a flexible, scalable, secure, robust, resilient networking test bed that we can develop and build new communication protocols, different algorithms, as well as proof of concepting the networking. So I wouldn't say that we have accomplished all these goals, that we made a big progress towards that direction. And then I will be describing each and every different development that we have done for each and every item that we have it here. And I will try to give you an idea what is next and what is coming up in a sense. So, but first I would like to go a little bit about what is unique and what we have built for CNN. And I would like to start with the open architecture. What do we mean by open architecture? Why it's important for the CNN project? So the open architecture pretty much can be described in two different sections. First of all, we have an open programmable software architecture, which allows you to operate at each layer. You can hide the details of each layer of the protocol stack. For instance, if you don't want to mess up with the physical layer, you can provide abstractions at the high level, for which you can use existing primitive building blocks. But if you want to, modify specific building blocks or blocks of elements, you can also do this. What it gives you is that you can define, add, and operate at different layers of the architecture, and then you can study different layers of the architecture. So you can build a physical layer test. Primarily, you can have a medium access control test, or you can just focus on routing and mesh networking capabilities. So you can do these different abstractions and enabling different parts of the modem. What is also enabling is that we can reprogram different parts of the modem. These devices have been developed based on the Linux operating system. So they're also natively supporting most of the internet architecture and the internet tools that you have available in the Linux kernels. So this is the software architecture and why it's unique to be enabling all these different features that is not possible with today's devices. On the hardware side, we have a swappable front end, a completely reconfigurable hardwares. What does that mean is that we can actually seamlessly integrate different transducers. So one thing that I think we need to be aware is that there is not a real single antenna that's covering all the communication frequencies that is using underwater, which we call these antennas are transducers. They're pretty much creating mechanical sound waves using electrical waves, and then they can actually do the vice versa. So what is limiting is that there's not a single transducer that can cover all these frequencies. So it is important to be able to support different frequency bands and different transducers, so you can actually swap those front ends, and you can be able to operate in different domains without requiring to redesign the whole hardware. Last but not least, also these devices have been designed to be able to recharge themselves wirelessly using these antennas and harvesting the wireless energy that is coming and sent through the acoustic channels towards them. So looking at it a little bit more in detail, so what does that really mean is that we have enabling with this structure also a spectral agility. What is that important is that we can actually operate in different parts of the bandwidth. We can make a trade-off between the distance and the data rate. So you can imagine that if you go further down in the range, you have to trade off the data rate. And if you're just going shorter on the distances, you can use larger bandwidths and you can have more data rate. So what we are enabling with this reprogrammable devices that is on the fly, it can actually make that trade-off in real time without requiring any external reprogramming or any other intervention from a user point of view. So it can actually capable of doing process in real time. It can switch its frequency, and in this way it can support high data rates at all times or optimal performance at all times. Also, these devices were specifically designed to be able to process in real time large bandwidth data. Now the question would be, okay, like where we don't have bandwidth large enough. So why do we have large data coming in, right? The reason is that even though the bandwidths are much smaller compared to RF domain, the granularity of the sampling is much higher because you're actually now using much smaller bandwidths, subcarrier bandwidths, or like precision, let's say. So the sampling ratio over to your bandwidths are much higher. So comparably, it's almost like terahertz or millimeter wave bandwidths type of data that's coming in real time towards your processing tool. So like one example would be like normally if you will have to have a fast Fourier transform in real time in Wi-Fi devices, you're just looking into a 64 subcarrier FFT. So in most of our implementations, when we do some sort of an OFDM, we have FFT sizes of 8,000 or 16,000 subcarriers FFT. So it's much more demanding compared to standard RF devices because of that imbalance between the sampling rates and the data rates, the bandwidths that we are dealing with. So this is just an illustration, a picture of our CNET modem that we have developed. As you can see on here on the right is where the modem are. It's pretty much have 6 different boards, which I'm going to explain very briefly. And then on the left, there is the battery unit that you powers this whole device. And then you have interfaces that can have external Ethernet, USB interfaces to control the device if it is required. And then you have the antenna coming out from this side. So this is a completely flexible communication platform that is fully programmable and being able to support different capabilities like artificial intelligence on the device, or can be integrated with UUV and ROVs that we have actually done some of that, and I will explain that. So just going a little bit, without going too much into detail, I would like to explain the hardware architecture. So we have a modular design hardware, and they have standard interfaces between those hardware. So what this allows us that we can actually swap or upgrade different sections of devices. How we break that? We break that modules in based on their responsibilities. So we have a baseband processor that has FPGAs, core processors. It can be also extended with GPUs. We have ADCs, DACs on a converter module with additional interfaces. And then we have the communication modules, which has the power amplifiers, linear amplifiers that has the pretty much the signal conditioning before things are sent to the transmission to the antenna. So you can upgrade all these different sections on different modules without changing anything in the architecture. So everything can be adapted to new applications and new domains. So going a little bit more into the hardware architecture. So if you look at it in the core, we have an FPGA system. We have actually running on a system on chip architecture, which has FPGA and ARM Cortex CPUs on top of each other. And that is giving us that we have a hardware and software programmability with compact packaging and low energy consumption with this decision. So we can have running everything on the same chip without requiring to interface different modules on the same device. One other decision that we have done is that, which is necessary to be able to run large bandwidth data that I was explaining before, is that in order to be processing that data in real time, you have to do most of the physical layer processing in FPGAs, which gives you much more discrete timelines on how you can process data, and then it gives you also much faster results compared to a general purpose processing system. So the logic that we have done, we break the system in 2 pieces that we have running pretty much the processing intensive functionalities, physical layer on the FPGA, which still can be software defined because we can actually software define the logic of the FPGA. We can reconfigure them in real time while everything is running in the hardware speed, which is actually the unique part that we are doing in this device. And then everything that is less time critical or non-time critical is running on the standard processing system that, higher layer medium access control or routing decisions can be addressed using the processing system in the device. So I will just skip this. This is pretty much the instances of different modules, what we use them in this version of the modem. Like we have a SoC board, we have implemented the ADC DAC converter module, we have different communication modules implemented, as well as we have signal and power modules implemented on the hardware domain. I would like to tell you a little bit briefly about the CNET architecture, software architecture as well. I mean, I kind of hinted that break between the medium access control and physical layer that is implementing an FPGA and processing system. Here it's actually is a little bit more pronounced, and then you can see that most of the non-time critical functionalities, the medium access control, network transport layer, are running actually in the kernel space of the Linux architecture. And this is important, and I will tell you why this is important to run on the kernel space. And then most of the application space, application layer, like video streaming, video encoders, sensor units, are running on the user space, while the physical layer and not time critical medium access control applications are running here on the programmable logic of things. And then you have a real-time device driver that is making this intersection between the two sections of the chip, which is the FPGA and the processing system. This is just an example of how an FPGA module is implemented. Specifically, we were looking into a simple zero-padded OFDM as well as a basic STR FPGA module. So the next thing that I would like to show is that why I was telling that we were implementing things in kernel module. Why this is important is that this is important because, in a sense, the hardware from the perspective, the front end and the communication protocols, everything of that you have implemented in the kernel level and the FPGA is looking like a standard interface when you look at from the application layer. So it's almost like your Ethernet card, you're seeing your CNET module, which you can actually see at the bottom here, that's appearing. So now, in addition to your Ethernet card of the module that you can connect it, you actually have also a wireless acoustic front end, a wireless ultrasonic front end that you can use it from any application. And you can send packets through the standard TCP IP links, and then make it pretty much a plug and play with the rest of the devices that you can use it. So this is why it's important to have this separation in the software architecture. With that, I would like to go briefly on the experiments that we have done. So we have tested these devices over the past 4 years at this point in different environments, in Boston Harbor, in Charlestown Marina, in the oceans, in the lakes. So we have been achieving relatively high data rates in the orders of 200, 250 kilobits per second in the links of 200, 300 meters. We have been also achieving much higher data rates, like closer to 1 megabits or 500 kilobits per second data rates in much shorter distances. So this is kind of was proof of concepting that what happens if once you have the spectrum agility and being able to use larger bandwidths, that you can get almost 10 times faster data rates compared to commercially available devices out there. Then if you look into some other functional tests, we have also done real-time reconfiguration. We were just showcasing that you can actually change the packet structure in real time, put more guard intervals in that specific case, but you can also change the whole communication protocol, and then pretty much you can send every packet in a different communication protocol if it is required, or you can send it in a different bandwidth if it is required, which gives you that, with that reprogrammability on the fly, you can actually do those things and without requiring any other programming or coding necessary. And this last test was primarily demonstrating that the wireless power transfer and then feasibility of that. You can actually charge these devices using multiple distributed transducers, and you're just doing some sort of a beamforming towards the receive antenna and then getting a charging enough that you can actually operate without the battery on the devices. You can wake up, do a sensor, sending the data that is out there. And that why this is important, then this means is that you can have actually batteryless devices deployed in the ocean that will not be outdated or out service without the depleting battery. You can always charge them, and then you can always operate them over the duration of the years. So we have done many different deployments, as I was telling. So this is one of videos that we have recorded in one of our experiments that we have done. This is done in the Marine Science Center of Northeastern University in Nahant, which is a little bit north of Boston. We have 2 devices deployed, and then you can see that we are transmitting, and we have a nice drone shot of these devices. And we were also driving a ROV around to be able to see the connectivity. And then you can see our team here on the boat also monitoring the devices here. So I think with this, I would like to briefly mention some of the other works that we have been doing recently, and then how we build up on top of this foundation of research, and then what is coming up next, in a sense. So with everything that we have learned from that CNET project, and with our experience with there, we actually developed something what we named Marena. So Marena is this software-based testbed for underwater wireless communication, networking, and research. So what we have done is that we have a testbed in the Marina that is allowing us to be able to do tests and experiments stable, repeatable, flexible, and robust fashion. And then what we have done is that we'll also have remote access to these nodes. So one of the challenges, obviously, living in the northeast of US, you have long winters, you have precipitation. So it's not always fun to go out there and do deployments and then being able to get data. So what we have done here is, for some reason, those are changing, but what we have done here is that we have a base station connected to these devices so that we can actually connect them remotely from anywhere that has internet, and then we can run different experiments on these devices and collect data in real time, which really speed up our research. And then we have been able to test many different communication protocols, develop medium access control developments, doing routing experiments. So it is really improving the streamlining the development for an underwater domain, which was primarily stuck with simulations due to the cost of devices, due to the extent of deployments existing today. So I think it's really a big step towards the right direction that we have seen, and we are very excited about having this testbed. And we'll just give you a little bit of overview what we have in that testbed. So we have a local control station which is sitting on the Marina base. And then we have software-defined modems underneath, deployed in different parts of the Marina that are cabled back to that the local control station. So the modems that we have used, and which I will be mentioning at the end of this presentation, is what we call HybridNet modem. So this is actually a spin-off company from our lab that is building these wideband modular modems through the DARPA funding that we have received in the past years. And we have used these modems to build that main architecture and being able to do this. And then we have a cloud server background that is sitting in an office in a different location that is controlling and connecting to this local control station. So any remote user that would like to use this testbed is going through our cloud server and then being able to connect to any of these modems in real time and then do experiments pretty much remotely at all times. Just looking into the hardware components and software components that I explained, is like we have cloud server, as I was explaining. We have these modems. It's hard to see them because they're at the bottom of the ocean, and then we have control station that is covering the connecting the ocean devices with the terrestrial domain. So if you look into obviously, this doesn't, it doesn't, everything is like flying colors. There's always some challenges. So one of the, I think, bigger limitations that we have never really experienced and that we have been really getting hard time controlling is the biofouling. So there is always some growth on the devices There is always like barnacles and around mussels, seaweed. So this is one of the challenges that is creating some blockage to the devices. And the other thing that I was explaining also, there is all this galvanic corrosion that might be happening. There is all this interference noise because there's chips moving around, there is the devices moving around. So those are the main limitations that you might be able to, you will experience if you're deploying such a device, such a network in the domain. But there are some certain solutions for all of these. So we have been really maintaining and really operating these devices without too much effort at this stage. So as I was telling, these devices really extend our experimental capabilities. So now, today, if you would like to get a channel sounding, this is happening in few minutes. In the past, we have to go there, deploy devices. It takes days, if not weeks, in many cases. So what we can do with these devices, we can do simple channel sounding. We can get real-time channel sounding at all times. We can have physical layer, medium access control layer, test, development, optimization. We can have real-time data set generations for AI and ML device, for AI and ML applications. We can try things like distributed MIMO. We can do applications like real-time video streaming and improving the real-time video streaming capabilities. Also, we can do mesh networking and like Wi-Fi like networking capabilities as well can be tested. So I'm just going to briefly give snapshots of some of the things that we have done, and then some of the experiments we have generated through this vehicle or a tool at this point that we can call it. So we've been using Marina to get channel sounding, as I was telling, physical layer and medium access control optimization. So we can generate different physical layers in real time, run it through the channel, get performance data, and then can compare them each other in different frequency bands, in different bandwidths easily. The other thing that I was explaining, that we can have data set generation for AI and ML applications, which I will briefly mention this project a little bit more in detail in the next few slides, so I will skip that for now. The other thing that we can do is really something unique is also we can have distributed SIMO systems. So you can have multiple receiver modems spread around in the ocean, and then you can have one mobile or fixed node that is transmitting to all of them. And then you can just combine using algorithms like maximum ratio combining, and then apply them to improve the bit error rate robustness or data rate, depending on what is you're really interested in. So some of the experiments that we have done here was that. The other thing that we have been doing is underwater wireless streaming. And this is actually something really fun because you can actually see the bottom of the ocean in real time from a YouTube channel. And you can watch the fish going through, all sent to to YouTube wirelessly with our modems that has at the bottom of the ocean. So this actually just was a demonstration that what we would like to do is that to showcase you can actually enable real-time data, even in the higher volumes like video in real time, and can get that data to any internet connected device anywhere on the world pretty much. So if you have your phone with you, you can just scan this HR QR code, and then you can go to our YouTube page, and you can see there's pretty much a live video at all times from our testbed that you can watch it actually. And then, excluding the fish is not really always there, but comes and goes pretty much. One other thing that we have been doing with our testbed is also we were studying different medium access controls. We have been trying different medium access controls in real time with different physical layers. And there's a good comparison of how we can achieve that networking capabilities in these devices, what is called software-defined underwater networking at this point. So overall, I think this really helped us to be able to build communication protocols, build physical layer, medium access control layer protocols, as well as developing AI ML models and many other applications. So it really streamlined our research towards real practical applications. So with that, I would like to briefly mention two applications that we have been recently working on with a few colleagues that we have, a few PhD students that we have been working on. I had pleasure working with them in the past year or so. So the first project that I'm going to mention is what we call SONAIR. SONAIR is that's real-time deep learning for underwater acoustic communication spectrum sensing and classification. So what we do in SONAIR is that we would like to build a AI-based underwater spectrum sensing device that can make an inference and find signals in real time and classify them in real time without processing them or using any other types of model-based decision-making algorithms or mechanisms. So I think why it's challenging, obviously, as I mentioned, underwater spectrum is not very efficiently used. So any sort of sensing the spectrum efficiently is really, really important for underwater domain. And then the inference and control of such resources or channels in underwater can also enable different applications, which I will hint at the end of this this section of the presentation. But what we really need is that we need solutions to be data-driven. They need to be doing things in real time, so we cannot just send data to a cloud. There's not really that sort of data rates or backend that we have in RF domain. So, and then we need to be models that is highly generalizable, so we can actually deploy in different parts of the ocean and being able to still perform at a level that can do the inference. So if you look into existing work out there today, there are some simulated representations of underwater channel. There is some signal detection using binary detectors, but there is not really a full model running in real environment and then collecting real data. So that was something that is pretty unique, that we think that has never been done in the underwater domain without, I think to the best of our knowledge, let's say. So briefly, some of the facts of the project is that we have collected a data set, relatively large. It's 7 days of data in 2 different locations. And we have used 3 different physical layer modulations in different bandwidths. What we have done is that we have developed 2 parallel deep learning stages, one for modulation classifier, and then second one for signal localizer, which is identifying the bandwidth. The first one is identifying what physical layer you're using. And what we do is that we're identifying in real time those devices. And then if you do that, actually, you can avoid the handshaking, and which I will briefly mention what I mean with that at the end of this presentation. So looking into the data sets, as I was telling, these are just 7 days of recording. It's relatively a small amount of data for a data-driven approach, especially for underwater domain that is changing from time to time quite fast. So here again, we used a version of the CNET modems that we have developed through the project for recording those data. And if you look into the specifics of data set, we have used 3 different modulation with varying bandwidths. And then we have a center frequency that is varying as well, so that we can actually have a generalizable model that can find and locate where these signals are coming in real time at which section of the network. So looking a little bit in the architecture, it's just without going too much into details, we are using an altered version of the VGG16 networks. Overall, what we do is that we have inputting 2 channels, IQ samples. Almost 400 IQ samples is enough to make this decision. So we don't really process the data. We just use raw IQ samples with very minimal pre-processing that is running in real time on the devices. And then in the modulation classifier, it can be classifying the what physical layer we're using the single class for entire bandwidth. On the signal localizer, which is you're finding the bandwidth, we're using a multi-out encoded binary vector for this as an output that what our VGG16 is spitting out that we are actually processing at the end. So just looking into a general architecture, what we do is that we are just giving these IQ samples without any prior knowledge, and we're just classifying what communication protocol, what bandwidth, and then combining these 2 decisions and then having a common decision at the end. So briefly looking into the decisions from results from 3 different days, you can see that if we are testing in the same environment and using a similar data set to the training, we have great results. We are getting close to 90% precision almost. If you're looking into same environment with a different setup that you move devices around, you're really getting still high performance results, regardless of the day, setup, or where the devices are moved. And then once you take the devices into a completely different environment with different setup, then you're actually seeing that your precision gets lower. And this is actually showcasing that in order to reach that generalizable model, you need more data to be trained in different settings. And this is something that we will be doing. This is just a kind of a proof of concept. Even with some limited data, you can actually reach almost 90% precision detectability, making inference on the models itself. So this is just showcasing the joint classification results. And you can see in the same environment, we are pretty much getting 98% for some of the cases for empty classes, or 72% for the worst case scenario for OFDM pretty much. The next step that we have done, okay, this is great. You're having a model that can do things in offline, but actually, can you do this in real time? Can you actually put this thing running on the modem in real time and can do this inference in real time? And that is what we have done in the second part of this project. We have moved the Sonair architecture into the R exchange of the GNU radio using the Onyx libraries that is available from explained in this cited paper in down there. And what we have done is that in real time, running GNU radio with these modems, we can actually detect what physical layer at what bandwidth we can detect, and then speed out from a spectrogram in real time that you're seeing. This was recorded in the real time. You can say, oh, this is OFDM, this is FSK, or this is MT, this is church spectrum. In real time, you can switch what you're detecting and what bandwidth. So I think the next step here is that a natural next step is that, okay, now we can define and infer things. We can do that in real time. The next step is we were looking at is, can we actually do a polymorphic communication? What that means is that, can we actually remove the handshake between the transmitter and the receiver pair, so that transmitter will, analogically to say, will send a receiver a sentence, let's say, okay, and every word of that sentence is transmitted in a different language. And then you don't tell your receiver what language you're using in every word. And the receiver will just get all these, words and sentence, and can make an inference and then adapt its receiver in real time to those transmitted signal without any prior knowledge. So to give you an example, imagine that we're sending a OFDM using QPSK in each sampling, and then in specific bandwidth. So with few IQ samples, we can infer that, and then we can adjust our receiver to be able to receive that inferred signals in real time. So in this way, we can actually have receivers that can work without any prior knowledge from the transmitter. So what transmitters can do, it can always send and change its own communication protocol, which makes them actually very resilient against eavesdroppers, very resilient against jammers. So there's not a real easy way to jam these signals anymore, because you don't really know what you're going to jam, because there is always changing, and then the receiver is always detecting what you're doing. So this is just a toy example of the bigger theme of things that we are looking. You can also do this inference for many other things, obviously, that can enable on these devices, but this is just showcasing what is possible in today's technology. So I guess I have one last thing before I wrap it up. So we'll briefly switch gears here, and then we'll briefly mention about something that we're looking to be able to connect the underwater devices with air devices as well in a different carrier, in a say. So what we have been proposing is that, can we actually use like visible light instead of like any other technology, or instead of having a gateway node that is always floating on the surface of the ocean? So why this is important is that with using visible lights, you can actually go through different mediums. So you can actually go through the water medium to the air, or vice versa, and then you can remove the requirement of a gateway node, a buoy per se. So this is something really, really interesting, because then you don't need a infrastructure deployed at all times, or you don't need your underwater devices to come to the surface to be able to connect and deploy, kind of send all these data to a data mole or to the rest of the infrastructure, terrestrial infrastructure. This is just a simple demonstration. I mean, a simple video of it that is kind of explaining. I'm not sure if this runs properly here. If not, I will just skip it, I guess. Yeah, looks like it's resisting here. So, but just to kind of emphasizing on what the problem is, that normally if you would like to connect an underwater drone and an aerial drone, right, you need this buoy that has both underwater connectivity and the air terrestrial RF connectivity. So you need to deploy this first to be able to connect these two devices. And this is really, really requires an infrastructure. It's almost like you have to deploy a base station somewhere, which is a little easier than a base station building, but still is could be costly and could be a lot of. So by using these devices, this technology, you can actually connect those two devices without requiring this buoy. And these buoys are also prone to some other facts, like people actually steal those buoys and then asking for ransom from government entities. So they're also prone and not secure for many applications as well. So if you look into the state of art, so there has been some work looking into this in the past. There has been like studies, done in very highly controlled test beds, requires lasers and precise alignments, and they're mostly limited in the simulation data. If you look into the alternative approaches to this problem, most of them they're very limited or very low data rates, or they're only working in one direction. They can only send data from one direction, so from the underwater to the aerial rather than the bidirectional. So those are very limited and kind of in a more experimental stage compared to what we have done at this work. So what we have built is that we propose a software-defined visible networking, which enable robust, secure, and self-optimizing bidirectional communication links through the air-water interface. It's specifically efficient and suitable for ocean dynamics without requiring any relay nodes in between. So that's kind of connecting two devices, as I was explaining before. So what we have built is that we built a additional front end to our CNET modems that can support the visible light front end. So we are still using the same architecture of a CNET modem that is integrated with a VLC front end that can support also. So now the CNET modem with this work is actually become a multimodal network, multimodal modem that can support both acoustic and ultrasonic, and also as well as can support optical visible light, to be specific in this case. So first, we have tested these devices in experimental studies in a water tank. So we have 3 different settings where we have first try them in different distances. We try them in different alignments. We have also changed the environment. And what we have done also, we have changed the distance between the water, the depth of the device that is in the water, and also the height of the device that's over the water to see the different effects of these parameters. First, we start our study to look into the different modulation schemes to understand what is a modulation scheme that can work better. And then we did a study that's comparing different communication modules. So to give you a sense, optical waves are they cannot send Q because these are non-coherent signals. They work on intensity modulation or some adapted orthogonal frequency division multiplexing communication protocol. So it's a little different than RF. Again, it's quite unique in that sense that has primarily non-coherent waves that has special receiver and transmission schemes needed. So we have compared these different communication protocols, including asymmetrical clipped optical OFDMs, DC biased optical OFDMs, cap modulations, and versions of the cap modulations that we have. Compared their spectrum efficiency, compared their SNR and beta rate performances with different settings from air to water and water to air. And then our conclusion was that in most cases, the cap modulation is performing better than compared to the rest of the devices. So we have done more studies with different distances, looking into the air-water channel distance, water-air channel difference. We have also modeled, we have a theoretical model, and then we were actually comparing our theoretical model with the experimental results, and we have seen a quite nice intersection between that, which is also helpful because we, at the end of this, we have built a simulation tool which we can use for future deployment studies that we can do for these devices as well. We have looked into the alignment. So what happens if you have a misalignment between the devices, how far you can actually support the alignment between devices. We have a study on that. We have been studying the water surface waves, so how the waves are affecting, how the anomalies that's happening on the surface of the ocean affecting this waves going through, because this is actually gonna be deployed in a real ocean environment, that you will see waves that is in the few tens of meters that's going on. So you have to really test it and see what is the limitations there in another way. Then we have also looked into the water clarity, which is also an important fact that we have tested into the even to the extreme cases. You cannot even see. So this is also another thing that might happen in the coastal environments. You have more sediments moving in the ocean, so you have water clarity is much lower. But we have seen even with very high sediments or very low water clarity, we still have good communication performances and good beta rate performances in both directions of the communication link. We have also studied the background noise. So we were looking at how the ocean, how different, light sources will affect. Obviously, the largest light source is that the sun, how the sun will affect. So we were looking into the artificial SNR and then how, experiments are done compared to a dark room with a light room, to kind of understand how different factors are affecting, how different parameters are affecting our communication protocols and communication performances. In most cases, we were getting a very robust and reliable communication link bidirectionally. Last but not least, we also wanted to try everything in the wild with the real devices in the testbed that we have in the marina. So what we have done is that we have tested different communication protocols, the DC, OFDM, as well as the CAP. And in this 1 meter short distance, we were able to stream 1 megabits per second data with almost 10 to minus 7 bit error rates. So that's kind of showcasing that actually this is a very feasible solution. And for this project, and the next step is that integrating those devices into drones, actually to be able to move it around and then see how it's actually operating in the real wild environment without any control on the top of the devices. So that is kind of concludes what I have for the parts, and then we'll briefly mention about the HydroNet, the spin-off that we have used this core technology to spin off. It is the company is called HydroNet. Is pretty much what we're trying to build is that trying to bring the internet underwater and then make the link between the oceans and the digital environment. So pretty much all those things that I was explaining in the applications, we're trying to address and enable that. And to do that, we are building these next generation wideband modular modems, including also mesh networks, Wi-Fi networks, as well as real-time video streaming capabilities. And we have built those devices that not only can do communications, but can also do in-water sensing, as well as in-water inference and data analytics on the devices. So we would like to provide a nervous system that connecting the sensors and take the pulse of the ocean and being able to connect the physical and the digital worlds in a sense with these applications that we're looking at. So this is something that ongoing, and then please feel free to reach out if you have, if you're interested in an internship or a full-time position in the company. With that, I will wrap up, and I will be happy to have any questions if you have. And thank you for your concentration and interest on this.
Thank you very much, Emrecan. So let's stop the recording first.